So in this question, we have an image to study before we read the question. It looks like we've got something like a half pipe, so kind of a trajectory here. It looks like this thing is going to go down, so we would expect it to accelerate and then slow down as it comes up. Later, it shows it doing that very thing and being launched. And what we suspect then is that this thing will launch, and it has this initial velocity that's given of 3 meters per second. This launch height is 0.4 meters. So we would expect it to take a parabolic path. And of course, there is symmetry involved, so that to return to this same height, the vertical velocity, the VZ velocity, will be 0. This time here will equal this time. This V0Z will equal this VZ in magnitude. So just some of the things we would take note before we read the question. So we've got a block of mass, 0.20 kilograms. Circular arc, a height h above the floor, slides along the track with no friction, so there's no friction. It leaves a height 0.4 meters at a speed of 3 meters per second, so everything we interpreted. So after it leaves the track, what is the block speed when it reaches its highest point of its motion? Well, we did gloss over this in our thinking, and that is that the particle is going to move upward, and as it goes upward, it's going to decrease its vertical speed to 0 at the top. So initially, there is a V0x and a V0z. Well, that V0x remains the same throughout. But as it moves along, Vx stays the same, but Vz gets smaller. And Vz is 0 at the top, so the velocity at the top is exactly equal to Vx. So at the top, the velocity of the particle is Vx. So that takes us back to our triangle. So here is V0, here is Vx, here is Vz, and this is V0z and V0x, the initial velocities. This is 30 degrees. We know the hypotenuse, we're looking for x. So this is the adjacent side, that's the hypotenuse, it would be cosine. So cosine of 30 is adjacent over hypotenuse, which is V0x over V0, and therefore V0x is V0 cosine 30. And V0 is 3, and it's cosine 30, and so we can simply use our calculators to solve for this. 3 cosine 30 is 2.598 meters per second. Now, just going back to check, if this is 3, this should be less, so 2.598, and so that's clearly 3.6. Now, just conceptually, we can eliminate 0, and we can eliminate 3. So that gets us to 50-50, just realizing, now not making the mistake of just talking about the VZ, because it does have a Vx when it's traveling, and not making the mistake of thinking it remains unchanged. So that is choice 1, or question 1. The next one, we have this projectile. So we have this initial height, which we could extend over like so. And again, through the principles of symmetry, we know this time is going to equal that time, and that at this height, this velocity will equal the velocity 0 there. Both the overall v, the vertical, and the horizontal components. And so we want to know which of the graphs would represent the projectile's motion. Of course, and again, we also remember that Vz is going to decrease its speed to 0. Vz will be 0 at the top, and Vx will remain constant. So now let's see the choices we have. The horizontal position. Well, a position graph, the things we can read are position in time. The slope, or the gradient, is delta x over delta t, which is velocity. And the area, xt, has units of meters seconds, which is not a useful quantity. So we can read position, we can read velocity. Horizontal position, notable here is that the slope is 0, which means the velocity is 0. So this says that there's no horizontal velocity. It doesn't move in the horizontal at all. At all times, the horizontal position is the same, and that makes no sense whatsoever. Because we can see in the picture, it has horizontal translation. The horizontal velocity, the slope of a position time graph is the velocity, but now we have a velocity time graph. And the things we can read there are velocity and time. The gradient of the slope is delta v over delta t, which is the acceleration. And the area is v delta t, which is meters per second, which gives us the displacement. So this says the horizontal displacement, the horizontal velocity is increasing. Now, what we said previously is the horizontal velocity should be constant. The Vx is constant because there's no horizontal forces acting on it. This says the velocity is increasing, so this one is also out. Now, the vertical velocity. What this one is saying is that at time 0, there is a positive number, like, say, plus 15 meters per second. And that number decreases until it reaches 0, and then that speed increases again, but it's in the opposite direction, and it actually even gets to be faster than it was originally. Now, if we look at the graph, well, we expect this decreasing to 0, as we listed, increasing back to that point, and then getting faster than it even was before it reached the top. So it looks like this one is the answer. This one says the vertical acceleration is positive. So in our framework, if positive is upward and negative is downward, and there's our tree indicating the ground, this is saying it's got a positive acceleration, doing this, getting faster as it goes up, and then all of a sudden, it just starts with this huge acceleration, and then it has a negative, so this is like a positive 10 acceleration, this is like a negative 10 acceleration. And what we know about projectiles is the acceleration is g is 10 up, it is 10 at the top, and it is 10 on the way down. Minus 10 in all places, it's a constant. It doesn't change signs. So this one is also out. Choice C. All right, so we've got this scenario, which we could just do before we even see a picture, if there is one, is launched from the top of a cliff at an angle 30 degrees below the horizontal. So we're looking at this situation, 30 degrees. So there's a negative V0z. And so we want to know what goes on with the horizontal displacement and vertical velocity component as a function of time. So what we know is that Vx is going to be constant. Vz is going to increase in magnitude, and V0z will be greater than 0. And it will increase at minus 10 meters per second squared. So that's the vertical velocity. We want to know what's going on with the horizontal displacement. The horizontal displacement, xt, we know it has constant velocity. And a constant velocity means a constant slope. So it will look like that. So let's take a look at our choices. Horizontal displacement, as we said, the gradient or the slope is delta x over delta t, which is the velocity. Constant slope, constant velocity. This looks correct. See the same thing with this choice. Choices C and D says the position doesn't change. So right off the bat, these two are out as options. We're at 50-50. Now we look at the vertical velocity, and the notable difference is that the first choice says that the V0 is a minus number. Let's say minus 5. And this one says V0 equals 0. And V0 vertically would only be 0 if it were dropped. So that's out, and our answer is choice A. Number 4. So before we even read the question, we can, since there's a projectile being launched at an angle, we have our V0, our V0x, our V0z. And if this projectile, this is vertical, V0z, or Vz will decrease to 0, then increase in the negative direction. Vx will be constant. So let's see, we've got a hollow plastic ball projected into the air. So that may be important that it's hollow. Significant air resistance. Now, air resistance always acts in the opposite direction of velocity. So that means for this particular drawing that if this is the velocity, then the air resistance is in that direction. The force of air resistance and therefore the acceleration due to that air resistance will be in the other direction. So what we expect is that there's additional acceleration acting on this in the other direction. So that means it's not equal to g. We would expect if we were to throw a ping pong ball and a golf ball with the same initial velocity, 45 degrees, the ping pong ball will reach its maximum height first because the air is slowing it down, as opposed to the golf ball.